again. Right, moving on to dynamics and inclined planes. So we're nearly at the end of forces and friction chapter, which does mean we only have 2 chapters of mechanics to go. So it shows what good progress we're making. So, no extra information to add. I think the book says something about remembering that friction is mu r, but we've just done all that work on that, so it doesn't really matter. So we'll just go straight to the examples. So a particle is held at rest on a rough plane which is inclined to the horizontal at angle alpha. Where tan alpha is equal to 0.75. Well, we know that 0.75 is actually equivalent to 3/4. So before I even do anything else, because I know that my angle is acute, that must be the opposite and that must be the adjacent if it were to be a right-angled triangle. So therefore, sine alpha would be 3/5 and cos alpha would be 4/5. So by writing that information down, means we're not worrying about anything. We're not using up more of our brain capacity while we're doing a question. We're getting things that we know out the way immediately. The coefficient of friction between the particle and the plane is 0.5. The particle is released and slides down the plane. So let's add in our forces. I don't know the weight of the particle, so the particle's weight down must just be mg, and obviously we've got our normal reaction of the particle. It's sliding down the plane, so that means we've got some acceleration. So that's the only difference in these questions, is actually there's movement rather than things being at rest. And we know it's a rough plane, so therefore there must be friction, which if it's sliding down the plane must be acting this way. Now I know that that's friction, but I'm now adding in multiple unknowns. What I do know is that friction is equal to mu r. Now I've already got information for mu, and r, it's probable that I'm going to use it in the question. So rather than writing friction there, I'm going to write 0.5 r. So mu r is just that I'm putting in 0.5, so don't forget that I've got that information. So, part A is to find the acceleration of the particle. Now, because I've got multiple unknowns, the likelihood is I'm going to need to set up some simultaneous equations, because I just have too much information that I don't know at the moment. I have acceleration that I don't know, I have my resolved force, my normal reaction, which I don't know, and I don't know my mass. So that's why I need to envision I'm probably going to set up simultaneous equations. So I'm going to resolve parallel to the plane first, because that actually is the one that has my acceleration. So I need to resolve, and actually this time something I haven't used for quite a while, because I've been dealing with things that are stationary, is I need to use that resultant force is equal to mass times acceleration. So parallel to the plane, I have this, the weight of it is what is pulling it down, so mg sine alpha, and what's pulling it up is the friction force, so 0.5 r, and that is equal to mass times acceleration. Great. Can't do anything with that right now, so I'll now resolve perpendicular to the plane. So I have r. Now, because I know that there's no movement perpendicular to the plane, I don't need to worry about this. I know that the resultant force is going to be equal to any force going in the opposite direction. So r must be equal to mg cos alpha. Well, now I've got that, I can substitute my value for r into my first equation. It means I'm eliminating the number of unknowns, because I'm removing that r, I already have m and alpha as unknowns already. So therefore, mg sine alpha, subtract 0.5 mg cos alpha is equal to mass times acceleration. I have a multiple of m in all parts, so I can cancel. And I know what sine and cosine alpha are from the work I did at the beginning of the question. So actually all I need to do is substitute 9.8, 3/5, 9.8 and 4/5 into my calculator and get that acceleration is 1.96 meters per second squared to 3 significant figures. Part B. Find the distance it slides in the first 2 seconds. Well, I have a unique value for acceleration, so I have a constant acceleration. So this is using our SUVAT formulae. Now the question says that it was released from rest, so therefore my initial velocity is 0. I know my acceleration is 1.96 meters per second. I know that the time I'm looking at is in the first 2 seconds. And what I need to find is the distance travelled. So I'm using S equals UT plus half AT squared. Slightly dodgy square there, but you know what I'm using. So S is equal to, well, 0 times anything is 0, plus a half times by 1.96 times by 2 squared. So therefore S is 3.92 meters in the first 2 seconds. Easy. All we need to do is just actually remember when something like this comes up to refer back to our SUVAT equations. Okay, so I'm going to move on to the next example. A paperback where it should be, perfect. Okay. A box of mass 2 kilograms is pushed up a rough plane by a horizontal force of magnitude 25 newtons. So that's where we need to be really quite careful, because it says a horizontal force of 25 newtons. So if we don't read it properly and we just look at pushed up a plane by a force of 25 newtons, then actually what we're doing is completely interpreting the question wrong. So it's a horizontal force of 25 newtons. Given that coefficient of it's inclined at a horizontal angle of 10 degrees. Given that the coefficient of friction between the box and the plane is 0.3, find the acceleration of the box. Okay, so let's add on our forces. So our weight is 2g. Got our normal reaction there. Friction, it's being pushed upwards. So if you imagine something's on a hill and it's being pushed up, even by a force underneath it, it's going to travel upwards. Okay? So friction is definitely going to act in that direction. We know the coefficient of friction is 0.3, so I'm going to write 0.3r so that we are removing, again, that unknown straight away. I'm going to need to resolve parallel and perpendicular, so I'm going to write all my parallel and perpendicular lines on. That one's going upwards because obviously the force is travelling up the hill. That is going to be 10 degrees as well, because you imagine this line and the horizontal force are parallel lines, angles in parallel lines that are alternate are equal. Perfect. So I'm going to resolve parallel to the plane first. So parallel, that force going upwards, and obviously we know it's moving upwards, so I need to add in my acceleration. Sorry. So 25 cos of 10 degrees. Subtract, so you've got friction coming downwards, and you've got the force downwards from the weight. So 2g sine 10 is equal to mass times by acceleration. So we're finding the acceleration, so we do need that information there. Now going to resolve perpendicular to the plane. So I've got R moving upwards away from the plane, and then I've got these two forces get down in the other direction. Again, I've got no perpendicular movement. That is in equilibrium, so this force must be equivalent to the sum of these two forces. So 25 sine 10 plus 2g cos of 10. Now you probably notice if you do look at the example in the book rather than just alongside my PowerPoint, that the angles that the book uses are sometimes slightly different. I think what I've drawn is clearer, but obviously if you want to have a look at the book and look why they're using 80 degrees, you can see that and see why, but I'd rather not use different angles if I don't have to. So obviously now I have a value for R. It's my only unknown here other than alpha, so I'm just going to substitute. So 25 cos 10 minus 0.3 lots of 25 sine of 10 plus 2g cos of 10, subtract 2g sine of 10 is equal to 2a. Yet again, it's just a matter of substituting all these values into your calculator. Just being careful with your brackets, because you're doing 0.3 multiplied by two different things. So just be really careful there when you're substituting it in. And then all of that will be divided by 2. And you'll end up with acceleration is 7.06 meters per second squared to 3 significant figures.